Welcome back, everybody. We're going to be doing the prerequisites for Dynamics, Part 2. I hope you guys saw the notes that were posted. I hope you survived the module test. I know it's the day right after. And we're going to start, we're going to be going pretty much exactly over the notes in the PDF. I'm going to be kind of doing them again here. And we're going to be starting with imaginary numbers. Okay. So, as always, please feel free to ask questions at any point. So we're starting with imaginary numbers, which come up in rotations most of all. That's why we do them. In Dynamics, there's often a rotational component to what you see, and that's where they're going to be most important for us. So let's start with the definition of the number I. And we can define I as the square root of -1, or kind of what we really mean by that is it's the number such that when you square it, you get -1. And of course, you guys know there is no such number. There's no such real number such that when you square it, you get something negative. So in a sense, so that's why they're called imaginary numbers. What the heck is this? So one way that you can think about it is almost as a notational convenience. It's a little notation thing. We're going to define this symbol I, and what we're going to do is wherever there's an I squared, if you ever happen to come across an I squared, this is what you do with it. And other than that, you keep the I parts, the imaginary parts, and the real parts, the regular number parts, more or less separate. And you work with numbers the same way you would otherwise do, and those are the two rules you keep in mind. Keep the real and the imaginary part separate. Wherever you have an I squared, replace it by -1. And a lot of amazing stuff kind of follows from those simple rules. So when we have numbers that have both a real and an imaginary component, we call them complex numbers. They have real parts and imaginary parts. And for some historical reason that I don't know, often people talk of a complex number, they write it as Z or Z. Okay. And so we're going to say that Z has a real part plus an imaginary part, and we write that as A plus B. So both A and B here are real numbers. And by multiplying B times I, this part here becomes an imaginary number. Okay? And we often plot these on a plane. So this number now, this number Z, it's one number, but it has two components. So it's almost like a little vector, right? That there's two numbers that make it up, A and B. And so we could plot it. If we plot the real part of Z on the horizontal axis and the imaginary part of Z on the vertical axis, then A would be, let's say that here's our number Z, and then this would be A, the horizontal component, and B would be the vertical component. Okay. And it turns out that that way of plotting it is going to become useful later. Often we talk about the complex conjugate. This is also something that becomes useful later. The complex conjugate of Z, defined, or not defined, but described by this star that I put here. This star right here. That means complex conjugate. And that just means take the imaginary part and flip its sign. If it was positive, make it negative. If it was negative, make it positive. So the complex conjugate of Z would be A minus IB. So that would be kind of this is minus b, that would be right here. So how do we work with these things? How do we work with these numbers? And what I said was that you follow two kind of rules. The two rules are first, that you keep the real parts and the imaginary parts separate. You keep track of them separately. And second, wherever you have I squared, that turns into minus 1. Let me highlight that. And with those two simple rules, you can just proceed with everything as normal. And I think in the notes I wrote, if you come up with complex numbers, if you take the eigenvalues of some matrix and things come up complex, keep calm and carry on. Meaning, you just follow these rules. And if you started with real numbers and somewhere along the way in your computation you got to complex numbers, by the time you get to the end, all the imaginary parts will have canceled and you'll be back to real numbers. So think of it as a notational convenience as you go through the computation. And I'll take you guys through an example. So for example, what does that mean? Suppose that we want to add two numbers. So let's say that we're adding two numbers that are complex. So Z1 is A1 plus IB1, and Z2 is A2 plus IB2. So they could be any two complex numbers. Rule is keep the real parts and the imaginary parts separate, keep track of them separately. So you would just add the two real parts and add the two imaginary parts. And this is what you get. And you'll notice that what we did here just follows the normal rules of multiplication and addition. Right? If I hadn't told you that I was the square root of minus 1 and that it has these special properties, what I've written here would be exactly the normal thing that you'd expect for multiplication and addition. So addition, very simple. How about multiplication? So let's do multiplication. So Z1 times Z2. So we said we use all the regular rules of algebra. We just keep the real and the imaginary part separate. And if we have I squared, we turn it into minus 1. So let's multiply A1 plus IB1 times A2 plus IB2. Okay. And again, if I hadn't told you that I is the square root of minus 1 and you were multiplying these, you might just expand these parentheses. So you would get A1 times A2 plus I squared times B1 times B2. Okay. So first it was this term times this term, then this term times that term. Does this highlight anything that I'm doing? Is that visible to you guys? That's my NEU equivalent of the laser pointer. Okay. So tell me if it doesn't work. Although I see nodding heads, so hopefully that helps. Okay, so the second term was those two multiplied. And then, of course, you want the cross terms, this one times this one, and this one times that one. Okay, so let's just put them all out. So we get plus I, oops, I have to remember to switch pens, plus I times B1 A2 plus A1 B2. Okay. And you remember the rule, I squared turns into minus 1. So this is equal to A1 A2 minus B1 B2 plus I times, let me just shuffle the, switch the order, B1 times A2. Okay, and so here we've got, this is the real part of the result, and here's the imaginary part. And these two rules that we had above, they're the ones that told us how to multiply the two complex numbers and give us the answer. So suppose that we multiplied z times its own complex conjugate. So that means that A2 equals A1 and B2 equals minus B1, because remember the complex conjugate, you just switch the sign of the imaginary part. What we would get, so let's say that Z is A plus I times B, and Z star is A minus I times B. So what we would get would be A squared minus B times minus B, so that's a plus B squared. And then plus I, A1 is A, B2 is minus B, plus B times A. So the one on the right cancels out. Right? This is minus AB plus AB. And all we get is the one on the left, A squared. I wrote here A2 when I meant to write A squared. And nobody corrected me, which makes me worry that people are kind of semi-asleep. So this is the result. And notice that it's the result of Z times Z star, a number times its own complex conjugate, is completely real, no matter what the number was. The imaginary parts all cancel out. And it looks a little bit like the length of that vector. Right? Because you remember when we were writing Z over here, the length of this vector is the horizontal component, A squared, plus the vertical component squared. That's the square of the length of the vector. So we can think of this as the length or the magnitude of Z, but squared. So I'm going to put this squared term out. So the complex conjugate, multiplying by the complex conjugate, turns things into real lengths. So what are more things that we can do with complex numbers? Well, mostly, as I said at the beginning, we're thinking of them in terms of rotations. That's where they're going to come up most. So why are they like a rotation? So imagine that you've got some number A. Let's say a real number A. And once again, here what I'm showing is this is the plane where the horizontal component is the real part and the vertical component is the imaginary part. So now let's take some number A. Let's take a real number A. And if we multiply it times I, we're going to get I times A, of course. And so now that one we would plot there, right? Because it's purely imaginary. It's the same length as A, so the circle that I drew has radius A. And if we multiply times I again, we're going to get I squared A. And I squared, what do we replace I squared with? It's minus 1. Thank you. So here I'm plotting minus A. Right? And if we multiply times A again, we get I cubed A. I squared is minus 1, so this is the same as minus IA. Right? So you'll notice that this one is the negative of that one, right? We flip it across the origin. Maybe I'll emphasize that this point is the origin. Okay? 0 real part, 0 imaginary part. And if we multiply times I again, we get I to the 4th of A. How much is I to the 4th? Well, I squared is minus 1. I squared is minus 1 multiplied with 2. Minus 1 times minus 1 is plus 1. So you get back. So multiplying times A is like going around. Sorry, multiplying times I is like going around a circle in steps of 90 degrees. In radians, we would call that steps of pi by 2 degrees. And that is the way to think about these things. So I told you, here I've given you an example of, an intuition of why imaginary numbers relate to rotations. But I said, they come up in dynamics and in matrices when we think about rotations. So let's do that more directly. Let's look at a matrix that is a rotation matrix. So in fact, we're going to look at this matrix. 0, 1, minus 1, 0. So this guy, if you multiply it by 1, 0, it turns that into 0, 1. And if you multiply it by 0, 1, it turns that into minus 1, 0. So if you think about what that's doing, this was 1, 0, and it moves it over to 0, 1. And if this point is 0, 1, it moves it over to minus 1, 0. So what I'm trying to do is remind you that this matrix that I'm showing you is the 90-degree rotation matrix. It multiplies things by 90 degrees. And somewhere here I have a picture of it. Yeah, it's this guy. So let me bring that over. Okay, so here's the picture of the 90-degree rotation matrix. So suppose that we ask for the eigenvalues and eigenvectors of this matrix. So you guys will remember an eigenvector is a vector such that if we multiply the matrix times that vector, if we multiply the matrix times that vector, we get that same vector back, a vector pointing in the same direction, just scaled by some number lambda. Right? But what are vectors for a rotation matrix? Every vector gets changed, right? There is no vector where if you multiply the matrix times that, it stays pointing in the same thing. So suppose you go to Julia and you ask it, what are the eigenvalues and eigenvectors of this matrix? Well, what Julia's going to reply is the following. It's going to say, oh, yeah, no, they do exist. And the first eigenvalue is I. And the first eigenvector is this thing, 1 over root 2 I over root 2. And the second eigenvalue is minus I. And the second eigenvector is 1 over root 2 I minus I over root 2. Yeah. There's a mistake in the PDF of the notes. I'm missing the minus sign, but I'll correct it and I'll repost it. So this is the point where I wanted to say or emphasize, keep calm and carry on. Because you might look at this and say, what the heck does that mean? You know, how am I going to work with this? What's an imaginary eigenvector? It's just a notational convenience. We're going to keep going. So the first thing to do is let's check that these, in fact, are eigenvectors. So let's check the first one. Let's multiply the matrix times that eigenvector. Right? So our matrix was 0, 1, minus 1, 0. I'm calling it m sub 90 for 90-degree rotation. And let's multiply it times 1 over root 2 I over root 2. Okay, so that's going to give us 1 over root 2 times 0 is 0, plus I over root 2 times 1. That's I over root 2. So we get I over root 2. And on the bottom, it's 1 over root 2 times minus 1, plus I over root 2 times 0. So the second term is just 0. And we get minus 1 over root 2. Which is equal to I times 1 over root 2 times I over root 2. Right? So on the top, for the top component, if we multiply this one times I, we just get this. If we multiply this one times I times I is minus 1, so we get this. So yeah, this complex eigenvector with both real and imaginary parts is in fact an eigenvector following the definition that we had of mv equals lambda v. And it's an eigenvector with this eigenvalue, lambda 1, the square root of minus 1. Yeah?
So for real eigenvectors, we could sort of conceptualize it spatially as like the basis where it was just stretched and shrinked. Is there like a way to conceptualize this spatially, or do you just kind of...
So I have a much harder time with this one because they're complex numbers. So in a sense, the magnitude of the eigenvector of this guy here, the magnitude of the eigenvalue, that is going to be related to how much you rotate. And so sometimes I look at this and I think, oh, this is a rotation in a plane. So what defines that rotation is the axis of rotation. So you could think of this is pointing in a completely, it's pointing out of the plane, right? This is not in the ordinary plane. It's pointing out of the plane. It's telling us the axis of rotation. That vector, when you rotate, doesn't change. And its magnitude, the eigenvalue, that tells you how much you rotate. But that's not really quite exact because the axis of rotation is actually just one-dimensional, and the eigenvalues could be complex, has both a real part and an imaginary part, so it's a little more mind-bendy than that, and I don't really have a good intuition to share, but roughly speaking. Yeah.
Just a trivial question. This matrix M is rotating clockwise, negative magnitude instead.
Yes. I always get confused as to, whenever I'm writing down a rotation matrix, I never manage to predict the sign correctly, whether it's clockwise or anti-clockwise. So, yeah, I'm not totally sure. Like when you rotate the bases, the data actually rotate the other way around because you've rotated how you look at your head. So pay no attention to the sign of my rotation, just pay attention to the magnitude of the rotation. Yeah?
Can you explain the vectors of variable rotation again?
Yeah, these right here, these up here?
Yeah.
Sure. So for these, what I did was say, what happens if we multiply this matrix times this vector? So if you multiply the matrix times that vector, on the top row, you're going to get 1 times 0. You're going to get 1 times 0 plus 0 times 1. So that will give you 0. And for the bottom row, you're going to get 1 times minus 1 times 0 is 0. And here is exactly what Toma was saying, my mistake. There's a minus sign that was missing. And that's why I plotted them wrong and it goes around the other way. Meaning, no wonder you were confused. Sorry about that. So the vector 1, 0 actually turns into 0, minus 1. And when we do 0, 1, we do exactly the same thing. So, and now getting that one right, that one turns into 1, 0. So 0, 1, turns into 1, 0. And can you see why multiplying the matrix times that vector would give you this? Yeah? Okay. Did that clear up?
Did you just choose those vectors?
Oh, you could have chosen any old vectors, but the vectors that I chose are actually the cardinal vectors, right? So in fact, 0, 1 and 1, 0, this is I hat, and this is j hat. Right? So there are usual Cartesian bases. So that's why I chose them to illustrate the rotation. Okay, so key thing to remember, suppose that you're doing some computation with this matrix, and suppose that you want to go into the eigenbasis to compute something and then come back to the regular basis. All the imaginary parts are going to cancel out. That's the keep calm and carry on part. If you start with real numbers, the things are going to end up canceling out. So let me take you through an example which I think might be a little confusing, but in a way, that's kind of the point. We're going to get into this thicket of i's, and then by the time we come out, everything will have been cleaned up. So if you don't follow the details, don't worry. That's the main point. That we're going to go through a thicket of i's and whatnot, and we're going to keep track of real parts and imaginary parts, but at the end, it'll all work out. So we had, let me go through that example. We had our matrix, our 90-degree rotation matrix, which we said was 0, 1, minus 1, 0. And its eigenvalues and eigenvectors were 1 over root 2, I over root 2, and minus I. You'll notice, actually, that these two eigenvalues are complex conjugates of each other, and that the two eigenvectors are also complex conjugates of each other. And that always happens. It turns out that if you take if you ask for the eigenvalues and eigenvectors of a matrix and you come out with complex values, they're always complex conjugates. And that's what helps everything in the end cancel out. So if you guys remember the generalized eigenvalue equation where we were talking about matrices, it looked like this. And the idea was this one, is that this is a matrix with the eigenvectors as its columns. That's V. And lambda was a diagonal matrix, meaning zeros and all the off diagonals with the eigenvalues on the diagonal. So let's write that out for M90, and I'm going to point out that this means that M, for any matrix M, you can write it as V lambda V times the inverse of V. And those were some of the transformations that we were doing in the linear algebra model. So let's write that out for this matrix M90. So M90 is the matrix V, that's taking the eigenvectors and packing them as the columns of the matrix. Right? So that's going to be 1 over root 2, I over root 2 times 1 over root, and the other column is I over root 2 times minus I over root 2. Right? So that is just these two eigenvectors put together into a matrix. Then lambda, the lambda matrix, and that one has the eigenvalues on the diagonal and zeros everywhere else. And then we want the inverse of this matrix V. So what's the inverse of V? So let's stop and compute that. So this is our matrix V, and we want the inverse of V. And for any for any 2 by 2 matrix, its inverse was given by this, which you may not have memorized, but if you do it often enough, it'll end up getting stuck in your brain. Doesn't matter if you haven't memorized it, you can always look it up. So let's do that for this matrix. So that's going to be 1 over root 2 times minus I over root 2. So that's going to be minus I over 2 minus, so that was this one times that one, minus this one times that one, so we get a minus I over 2. Should have done that. Minus I over 2. And we flip, now we're going to do this part. So we flip some of these values. So minus I over root 2 here, 1 over root 2 there, 1 over root 2 here, I over root 2 here. And this is where we're getting into a thicket of i's. And those of you that are copying this down, I really don't know why you're doing it, but if it makes you happy, go ahead. So we can keep going through this, and this is going to end up looking like the following. I'm going to copy it out. Oh, by the way, one interesting thing to point out is that if you have 1 over I, you multiply times I on the top times I on the bottom. This is I over I squared, so this is equal to minus I. So if you have an I on the bottom, you can flip it around like that. So what we're going to end up with by the time we go through using that inverse and writing it all out, we're going to end up with this, that M90 can be written as I over 2 times 1 I minus I 0 0 minus I. Remember I told you we would be getting into a thicket of i's. We're in the middle of the thicket. And this here is lambda. And these two, they're not exactly V and its inverse, but they're really about changing bases. Right? That's what they're about. So the one in the middle, lambda, That's the one that tells us what the matrix really does. And because it has eyes, that's the one that it's saying it's a 90-degree rotation. Remember when we said all the way back here, oh, multiplying by I is like a 90-degree rotation? Well, that's exactly what we have here. Right? We're multiplying by I and by minus I, 90-degree rotations. So let's suppose that we wanted to do a 270-degree rotation. We might say, well, let's take that thing in the middle, and let's, instead of having I and minus I, let's cube each of those. Because that would be like 90-degree rotation, another 90-degree rotation, another 90-degree rotation. That would be like a 270-degree rotation. So the claim is that a 270-degree rotation matrix is going to look, we have exactly the same transformations, the same basis transformations, except that now we have I cubed here, 0, and minus I cubed here, minus I, minus 1, minus I, 1. Okay. And this is where the claim that, oh, if we look through this, all the imaginary parts are going to cancel out. We went into the eigenbasis so that over here we could say, oh, the matrix is pretty simple. It's just multiplication by I. And cubing it or taking its square root or anything like that is simple because we're in the diagonal basis. So that's how we computed this 270-degree rotation matrix. Does it really come out? When we multiply these three things, do the imaginary parts come out? And do we end up with a real matrix that represents 270-degree rotations? So let's go through that. So I cubed, well, that's I squared times I, so that's like minus I. And minus I cubed is like minus 1 times minus I. So that's like I. So this is what we're looking at. And let's just go through those matrix multiplications. Or actually, given the time, I'm going to claim that if we go through those matrix multiplications, and those of you that still don't have like matrix multiplication totally seared into your brain, this is a great exercise to do. Just go through those. And what you'll find is that this M270 ends up being this matrix. And indeed, all the I's cancel out. If you keep calm and carry on, everything will work out. I promise, for everything in general, not just math. Okay. So here's the M270. Here, I could copy, yeah, I'll copy them over just to put them in the right place in the notes. Or I guess not, because I ran out of space. So I'm going to ask you guys to look at them here. So here are those two matrices, the ones that we just made. And one of them rotates 90 degrees in one direction, and the other one rotates 90 degrees times 3 is like 90 degrees in the opposite direction. Okay. So the main point of what I was trying to take you through is if you stick with those rules, you keep the real parts and the imaginary parts separate, and wherever you have I squared, you turn that into minus 1. You start with real things, things will work out. That was key point number 1. Key point number 2, imaginary numbers are about rotations, especially when it comes to matrices. So I'm going to go on to the next topic, Taylor expansions. So any questions at this point would be particularly good to address. We're going to do Taylor expansions, which sounds like something completely different. And then the last thing we're going to do, which is something called Euler's formula, will actually bring all of these things back together. So let's do Taylor expansions. All right. So Taylor expansions are a way of thinking about function approximations. Suppose that you have a function that's f of x. So let's say we have x and f of x. And let's say that f of x looks something. It could be anything. And suppose that that function is complicated and difficult to work with. You might want some expression, some description of that function that is easier to work with. And maybe you say, oh, what I'll do is I'll work with an approximation of that function, something that is pretty much like it, but a lot easier to work with. So what are some approximations that we could do? We're going to make approximations in Taylor expansors. When we make an approximation, we always do it around a particular point. And we make approximations that are good when you're close to that point. And the further away that you go, the less good the approximation is going to be. So the first approximation for what f of x might be around x of 0, you might say, oh, I'm going to do a really simple approximation, which is, I'm just going to pretend that f of x, that this function, which actually changes quite a lot, I'm going to pretend that it's just a constant. What constant should I choose? Well, I'm going to choose the value of f at x naught. I'm going to choose whatever this value is. So that green dashed line, that's our initial approximation. And obviously, so that's what we call the 0th order approximation. It's a function of x. You give me a value of x. For any value of x that you give me, I can tell you what the value of the function is. Right? So I'm writing it down as f naught of x. It's a function of x. But it's a constant. It is f of x naught. And notice here, this is important. Here when we write f of x naught, that means we've evaluated f. It's a particular number, some constant number. Okay? And when x equals x naught, it's perfect. We've got exactly the right answer. And if you're really close to x naught, it's kind of okay. And the further away from x naught you go, the worse it is. Obviously, that's not really very good. So let's do a little better. You could say, oh, how about instead of approximating f as a constant, let's approximate it as a line. So what line should you choose? Well, how about choosing the line that goes through f of x naught and has the same slope as the original function f at x naught? And you can see that the blue approximation stays close to the black for longer than the green approximation, right? We did a little better. So, sounds reasonable. So, what function is that going to be? So, we're going to call that the first order approximation. Okay. And that's going to be a straight line. The equation for a straight line, Stephen was talking about it, right? It's mx plus b. So, it's some constant plus the slope times the value of x. So we're going to write it as follows. We're going to write it as f of x naught plus x minus x naught times the first derivative of f evaluated at x naught. Very important to note that once again, this thing is a constant. Right? Once you tell me what f, the first derivative of f is, and once you tell me what x naught is, and I plug that into that first derivative, I get some number out. So this is a function of x. The only thing that's changing here is x over here. And the claim is that the thing that I've written down is like the blue dotted line that I jotted. So let's see that. Let's just check, right? The claim is that this approximation f1, what's the value of f1 at x naught? So that means evaluate f1 when x equals x naught. When x equals x naught, well, when x equals x naught, that term goes away, right? Because you get x naught minus x naught. And you're left with just the value of the original function at x naught. So indeed, this blue approximation crosses this black dot that we had right here. And how about the slope? So let's take the derivative of f1. So f1 has two terms. What's the derivative of the first term with respect to x? person with the pink cap on backwards. The derivative of this first term, this is derivative with respect to x. How much does it change as you change x? Key thing, this thing is a constant. It's not a function of x, right? F of x naught is just a number. What's the derivative of a number with respect to it? 0, exactly. Right? The derivative, what's the slope of the green dotted line? 0, okay? So the first term just goes away, and so the derivative is going to be the derivative with respect to x of the second term, x minus x naught f prime of x naught. And what's the derivative of that? So let's just expand the thing inside the brackets. So it's d by dx of x times f prime of x naught minus x naught f prime of x naught. So that's just the derivative of the first one minus the derivative of the second one. So what's the derivative of the second one? I'm going to come back with you in a think. So derivative of this term right here. So if you look closely, oh, you guys actually see the highlighting? Yeah? Oh, okay, great. So this doesn't depend on x, right? There's no x term here. So this is another constant. So that's 0 too. Okay, great. So we can get rid of that one. Goodbye. And what's the derivative of the first one? F prime of x naught. Yeah, because f prime of x naught is a constant. Right? So we're just asking, what's the derivative of, the derivative with respect to x of m times x? It's just m, that's the slope, m is the slope, and in this case, the slope is f prime of x naught. So that's why I was emphasizing, once you put the x naught in, these are just numbers, they're just constants. So what that all came out to was that this thing was equal to f prime of x naught. So what we've just checked is that indeed this blue function, f1 of x, it goes through this point, right? Because f1 of x naught is f of x naught, and its slope at that point is the same as the slope of the original function at that point. So in other words, what we wrote down in blue is indeed like the blue dashed line. So let's do one more. So we did the 0th order approximation, then we did the 1st order approximation. Now let's do the 2nd order approximation. And the 2nd order approximation is going to look a lot like these first ones. Oh, I already did the green. I'm going to write it as f of x naught plus x minus x naught times f prime of x naught. And remember, these things are constants. Let me just write one more thing down and then I'll come back. And then I'm going to add another term that looks like this. 1/2 of x minus x naught squared times the 2nd derivative of f evaluated at x naught. Yes?
The reason why we did the derivative for the first order was that just to see how well the line fit.
So we're trying to make approximations that are better and better. As I'm adding more terms, so this was an okay approximation, kind of, but kind of sucky. This was a little better, it was the blue line. This one is going to be even better. And as we keep adding more terms, there are better and better approximations. And in particular, the range over which there are good approximations is going to get bigger and bigger. So that's why we're adding more terms. And what we're going to do in the next page actually is add an infinity of terms. And in fact, if you add an infinity of terms, this way of writing down a function becomes identical to the function. The range over which it is a good approximation is infinity, and it's another way to describe the function.
Okay, so we just took the derivative just to see how it worked out.
And in particular, we took the derivative of that blue function of f1 of x because the claim was that what I wrote down in symbols was the same as that dotted blue line, where the dotted blue line was defined as the straight line that passes through f of x naught, right? It touches that black point, and has the same slope at that black point as the original function. That's what we were checking. So this second approximation is now going to look like a parabola because it's got a squared term. So it might look something more kind of like that. And again, the range, how wide the range is over which it hugs the black line is going to be broader than the blue one, and of course much broader than the green one. And the more terms that we add, the better the approximations are going to be. So this time the claim is that this brown function that I jotted down, f2 of x, has the same value as the original f of x at x naught. Right? It goes through that black point. But it has the same slope at x naught as the original function. And the claim is that it also has the same second derivative as the original function. Right? And that's why as we add more and more of these, we're describing more and more of the curvature of f, and we're saying, and those things in our approximations are equal to what the original f had. So let's go through those claims. So claim number one, that f2 of x naught is equal to f of x naught. Is that true, yes or no? How do we tell? Well, we just plug x naught into this formula. So this second term, what's the value of that second term when x equals x naught? What do you think?
0.
0. What?
X naught minus x naught 0. So
Exactly. And how about this term?
same.
Same. Okay. So we've just shown that f2 of x naught is indeed f of x naught. In other words, the brown expression, the brown f2 of x, does go through the black point. Okay. Now, let's take the first derivative. So the first derivative of f2 of x by dx, and I'm going to evaluate it at x naught. I'm going to ask what's its value at x naught. So what's the first derivative? Help me write it down. Rebecca, go for it. So let's just go term by term. So let's ask, what's the first derivative of this term?
That's a constant.
That's a constant.
So 0.
0. Okay. So we don't need to worry about that term. How about the first derivative of this term?
Well, if you multiply x naught by the function of x naught, that's also 0. So it would be the derivative of x times f of x naught.
Yeah. And what's the derivative of x times f prime of x naught? F prime of x naught being a constant. Somebody else help Rebecca out? F prime of x naught. Exactly. So this is exactly what we had done with the blue function. Right? So this is like we're saying, oh, this f prime of x naught is almost like m, so we're asking, it is a constant that we could call m if we liked. So we're asking, what's the derivative of x times m? What's the slope of this function xm? The slope is m. So what we get out of all of that is that for this second term, so the first derivative of the first term was 0. For the second term, we get f prime of x naught. And now we need to take the derivative of the third term. So what's that going to be? So the first derivative of this third term out here. So let me make a little corner over here. Let's see what d by dx of a half x minus x naught squared times f double prime of x naught. Now I want to remind you, f double prime of x naught, that's just a number. That's a constant, right? We could call it m if we liked. Allie. Sorry, say it again.
F double prime x naught times x minus double prime x naught. No,
I-
that first term.
Is that what you meant? I don't know if that's what you meant, but this is what it turns out to be. So let's go through. So for some of you, you'll be looking at that and thinking, yes, I can do that derivative. Those of you that are looking at it and the derivative isn't coming quite easily, there's a reminder to do the calculus exercises and to refresh your calculus. This should be relatively straightforward. So the half just comes out because the half and the f prime of x naught are constants. So this is the same as a half times f prime double prime of x naught times the first derivative of x minus x naught squared. And here we're going to apply the chain rule. So let's say y equals x minus x naught. So we're asking for the first derivative of y squared, right? where y is a function of x. And the chain rule tells us that that's dy squared by dy times dy by dx. And that might have gotten a little too small for you guys to see, so let me zoom in a bit. So what's the first derivative of y squared with respect to y? 2y. Okay, so this is equal to 2 times y. And what's dy by dx? The first derivative of y with respect to x. So y, this function, what is its slope? If you plot this function y as a function of x, what's the slope? 1. Yeah. And this is straightforward, right? Okay. So that means that this first term here, that was 2y, the second term was 1, so all we get is 2y, and y is x minus x naught. So what we get at the end of all that is 1/2 f double prime of x naught times 2 times x minus x naught. And how much is that when x equals x naught? Zero. Yeah, because these are just constants, and if you set x to be equal to x naught minus x naught is 0, so the whole thing goes away. So that means, at the end of the day, that was a long set of steps. But what we got was that the first derivative of this Brown function at x naught is indeed f prime of x naught. In other words, the Brown function has the same slope as the original at x naught. And now we want to take the second derivative. So let's take the second derivative of the Brown function. What's the second derivative of the first term? Meaning, if I look at f of x naught, what's the second derivative of that with respect to x? Let's take a step back. The second derivative is the first derivative of the first derivative of this thing. What's the first derivative of this term? 0. So what's the second derivative of the term? 0. Okay, so we can forget about that one. What's the first derivative of this term? We just did it. We've still got it written down. It's f prime of x naught. Right? And f prime of x naught, is that a function of x? Is that a constant? It's a constant. So if we take the derivative of that to get the second derivative, what do we get? 0. Okay, so the second term is going to go away too. Yay. And we're only left with the third term. What's the second derivative of the third term? So let's think about it again. And let's do the same thing that we did before. We're going to say y equals x minus x naught. Okay. And let's take the first derivative. Okay. And we're going to ignore the constants. So I'm sorry about the green highlight. Okay. can't undo it now. But I'm just going to ask for the second derivative with respect to x of y squared. Because the half and the f double prime of x naught, they're constants, right? So they're just going to multiply whatever answer we get out. Okay. So this is d by dx. This is the derivative of y squared. And the chain rule tells us, we use the chain rule on the inside part, this is dy squared by dy times dy by dx. And what did that come out to? So what's dy squared by dy? What's the first derivative of y squared with respect to y? 2y. So this is d by dx of 2y, and dy by dx was the first derivative of y with respect to x is 1. Okay, so what we want is this, and y is x minus x naught. So let's replace y times x minus x naught. Okay, and what's the first derivative of that? What's the slope of this function with respect to x? I'm going to take the votes. I think I heard people say 2. Yeah, it's 2, right? Okay, so what we get out of this is a 2. And that 2 multiplies the half, and so what we end up with is that the second derivative, remember the second derivative of the first term was 0, the second derivative of the second term was 0, so we're only left with the third term, is equal to f double prime of x naught. Because when we took the second derivative of this whole thing, we came out with 1. It was a 2 times the half is 1, and we're only left with the f double prime of x naught. So that was a very long path to saying, yes, the second derivative of the Brown function, as we've written it, has the same value as the second derivative of the original black function. So you can keep going with these terms. And what you end up with, if you just go infinitely, is that any function f of x can be approximated as the sum of terms that look like that. And we take an infinity of them, where each of the terms looks like 1 over n factorial times x minus x naught to the n times the nth derivative of f evaluated at x naught. And this expansion is called a Taylor expansion. It's another way of writing f of x. So about these terms, n factorial, 0 factorial is defined as 1, just to be clear. And in general, n factorial means n times n minus 1 times n minus 2 times n minus 2, and so on and so forth until you get to 1. So for example, the first term of this, let's just go through it. When n is 0, the first term would look like 1 over 0 factorial, that's 1. X minus x naught to the 0. Any number to the 0 is 1, so this is also 1. And the 0th derivative of f of x is just f of x itself. So the first term comes out to f of x naught. So the first term is the green function that we'd written over here, right? And let's look at the second term. The second term, now n equals 1. So that would be 1 over 1 times x minus x naught times the first derivative of f of x evaluated at x naught. Or in other words, the other way that I wrote it was f prime of x naught. So n equals 0 term, n equals 1 term, the n equals 2 term is going to look like 1 over 2 factorial is a half times x minus x naught squared times f double prime of x naught. And you can recognize the terms that we were writing before. So what I'm trying to do is show you that the formula that we've got here that goes out to n equals infinity actually corresponds to the thing that we'd written before. And in fact, if you take these derivatives, as you take the derivatives, every time you take a derivative, one of these exponents comes down, and the exponent gets reduced by 1, right? Because the derivative of x to the n is n times x to the n minus 1. So as we take those derivatives, n comes down to multiply, but now becomes n minus 1. The next derivative, we get an n minus 1, and the exponent becomes n minus 2, and so on and so forth. And that's where the factorials come from. And if you go through it, if you go through all of these, you can see that these match, the nth term matches the nth derivative of the original function. Okay, so with this, you can approximate functions more and more closely. So for example, here I'm showing you in the dotted line, this is the sine of x plotted in Julia. And then the brown line is, this is all around pi over 6. And the brown line is just the constant, is f naught. The green line is the straight line that follows those terms of the Taylor expansion. It has the same slope as sine of x at pi over 6. And then we also have the parabola. And as you can see, kind of in the way that I was trying to sketch out, the parabola hugs sine of x over a greater range than any of the other functions. And as you keep adding terms, you hug sine of x over a greater and greater and greater range. So the approximations get better and better and better. Okay, so we said that's a way to work with some approximations. Why are we using those approximations? So there are two reasons. First, they're easy to work with. So this function, the function that we've got here, that's a polynomial. They're just powers of x. So there are many cases where this thing is much easier to work with than, for example, if you had cos squared times the tan of x or something complicated, this approximation is easier to work. Second, in dynamics, and this is why we're doing it as prerequisites for dynamics, we're often looking at what happens around stable points, what happens around a particular point. And approximations that are local to that point can be much simpler than the original function and give us a lot of insight as to what goes on. So we're going to be using Taylor expansions a lot in dynamics. And the third reason is what I'm about to show you. And it's the last thing that we're going to do before we're done at 250. And this is what's called Euler's formula. And for those of you that you've seen it before, the magic is gone, but this is my favorite thing to teach of all time. So I hope I can, if you haven't seen it before, I hope you'll have fun. Okay. So what we're going to do is we're going to do Taylor expansion of sine of x, cosine of x, and e of x around x equals 0. And then we're going to compare. So we know that we're going to need the derivatives of sine of x, cosine, and so on. So let's take a bunch of those. So sine of 0, what's the sine of 0? Sine of 0 is 0. Yay, people remember. Awesome. Woohoo. Okay. And the first derivative of sine x is cosine of x. You got it there in the notes. And the cosine of 0 is 1. Okay. So here I'm always evaluating at x equals 0. Right? And actually, let me write it as first. Oops. Evaluating at x equals 0. The first derivative of sine is cosine, and cosine of 0 is 1. So let's take the second derivative. So that's just the derivative of cosine. And what's the derivative of cosine? Sorry, say that again? Negative sine. Okay, so it's minus sine of x. And when x equals 0, that is 0. Okay. Last one, third derivative of sine of x is we take the derivative of minus sine x. Derivative of minus sine x is cosine evaluated at 1. Sorry, evaluated at x equals 0 is minus 1. So that goes to minus 1. And now we've got a cosine x. And so the next derivative of that is going to be sine x again, right? Because the derivative of cosine is minus sine, and we loop back. So you can see that there's going to be a pattern. As we go through all the derivatives and we keep going, it goes 0, 1, 0, minus 1, 0, 1, 0, minus 1, 0, 1, 0, minus 1. It just keeps going forever. So let's do the same for cosine of x. Cosine of 0 is 1. The first derivative of cosine of x is minus sine x. And at 0, that goes to 0. The second derivative of cosine is minus cosine of x, and at x equals 0, that's minus 1. The third derivative, we're just keeping going. Oops, why did I write cos squared? Is minus sine x, so this is sine x at x equals 0, 0. The fourth derivative of cosine x is cosine x at x equals 0, that goes to 1. So you can see it follows the same pattern, 1, 0, minus 1, 0, 1, 0, minus 1, 0, except it's a little out of phase, right? They're not exactly in sync. One's a little in advance of the other. And so on and so forth. So if we use those to write out the Taylor approximations, sine of x, actually, let me move things a little bit, give it a little bit more space. So let's write the Taylor approximations for sine of x and cosine of x. So sine of x, we're going to start with the first term. So the first term is just the value of this function at x equals 0. It's going to be 0 plus the next term is x minus x 0, x minus x naught. In our case, what we're doing right now, x naught is 0. So x minus x naught is just x. Then it's going to be x times the first derivative. Ooh, that's not what I wanted to do. Times the first derivative. The first derivative is 1. So we just get x alone. Plus the next term is going to be 1/2 x squared times the second derivative. The second derivative is 0, so the next term is 0. Get a big fat 0. The next term would be 1/3 factorial. If you go back to the formula that we're using here, we're now using the next term for n equals 3. So the next term is 1/3 factorial times x cubed times the third derivative evaluated at x equals 0, and that's minus 1. Okay. So we actually get a minus here. And you can see that there's going to be a pattern as we just follow those things. And it's following the same pattern as the derivatives, right? So you've got 1, 0, minus 1, 0, plus 1. And as we go, we're going up the terms of this formula. So let's do the same for cosine of x. Cosine of x, cosine of 0 is 1. And then it follows the same pattern. The next term is 0, because now the first derivative is 0. The next term has a minus 1/2 x squared. And that minus comes from here. The second derivative evaluated at x equals 0 is minus 1. The next term is 0 because this derivative is 0. The next term has a minus in it. Sorry, a plus now. 1 over 4 factorial x to the 4th, and so on and so forth, and we keep going. So let me write them out. So sine x is approximately 0 plus x plus 0 minus 1 over 3 factorial, just following that pattern, plus 0 plus 1 over 5 factorial, x to the 5, 0, and so on and so forth. And the cosine of x is approximately. Sorry, say that again?
There's no word on the screen. If you just press it.
Oh, thank you. Cosine of x is 1 plus 0 minus a half x squared plus 0 plus 1 over 4 x to the 4th plus 0 minus 1 over 6 x to the 6 factorial. All of these are factorials. X to the 6th. And now let's do e to the x. Now e to the x, its derivative is just e to the x. That's how we found the number e. Right? That's how we define the number e. So that guy's easy, because that means that all the derivatives over here, we can forget about those, and we're going around x not equals 0, so we can forget about this. So it's just terms that look like 1 over n factorial times x to the n. So this guy looks like 1 plus x plus 1/2 x squared plus 1 over 3 factorial x to the 3 plus 1 over 4 factorial x to the 4th plus 1 over 5 factorial x to the 5th, and so on and so forth. You can start to see that there are some patterns that kind of like match a little bit, right? So now for the super fun thing. Let's just do e to the ix cosine x and I times sine x. Okay. So cosine x we already have. That's the black one. It's right there. Right? An I times sine x, well that one's easy. We just multiply everything times I. So we've got an I here. We've got an I there. E to the ix is a little bit more interesting. Right? So e to the ix, we put an ix here. Wherever we had x, we now multiply times I. So for the next term, we're going to have an I squared. I squared is minus 1. Right? So that means that this becomes a minus 1. The next term we have I cubed. That's minus I cubed. And minus I cubed, I cubed is minus I, so this becomes minus I. The next term will have an I to the 4th. I to the 4th is 1, that's I squared times I squared. And now we keep going, and you can see how the pattern goes. The next term is I to the 5th. That's just like 1I. The next term is I to the 6th. That's like a minus. And the thing is, if you sum cosine x plus I sine x, what you get is that they all match exactly. If you sum the first two, you get the third one. You get e to the ix. And that's true for as many terms as we can write. So what that means is that e to the ix is equal to cosine x plus I times sine x. It's another way of writing these numbers. And here's the super fun part that I love talking about. If we put in x equals pi, what's the cosine of pi radians? So pi radians is like 180 degrees. What's the cosine of pi? Is minus 1. And the sine of pi, the sine of 180 degrees, is 0. So what we've written out, the top one is the general formula, but if you look at the bottom one, we've got two irrational numbers defined completely differently. Pi is the relationship between the circumference in a circle and its radius. E was this crazy thing where we said, oh, when we take the derivative, it's equal to itself. They're irrational numbers. They have infinite numbers of decimal digits. But when you combine them with the square root of -1, we take e to the square root of -1 times pi, all those numbers cancel out, and it becomes -1. Exactly. This is amazing, right? This is incredible. I don't have a good intuition as to how this works, that everything cancels out so beautifully. When you put in the square root of -1, which is an imaginary number. It's a number that doesn't even exist. And it turns out to be incredibly useful for rotations. So I like telling the story of this student that I met at Caltech who had memorized pi to 300 decimal digits and had memorized e to 200 and something decimal digits. And I asked her, how did you feel when you learned that e to the I pi was -1? And she said to me, it was the best day of my life. So the important thing about this formula, and this is the last thing I'll tell you before I let you go, is that it means that when we wrote out this real and imaginary plane, and I multiplied by I, that didn't just work for multiplying by I. It means that any number z that's a plus ib, we can express it as r e to the I theta, where theta is this angle that it makes. And that makes it a lot easier to work with, and we'll be working with those numbers as we go. All right, that's the end of the prerequisites, and we use all of this next week. Here, let me turn the recording on.